So I looked up here at the remainder theorem. This is so, I think, convoluted. Let's just try to go through it. Let P be a polynomial function in X, and A is any real number. Then there exists a unique polynomial Q such that I can write P, so I can write my original polynomial as Q times X minus A plus some P of A. It's true for all X. That is, if a polynomial is divided by X minus A, the remainder is the value of the polynomial evaluated at A. So, again, all that at the beginning is very hard to understand, I would say. But right there, that sentence is the main one. When a polynomial is divided by X minus A, the remainder is the value of the polynomial evaluated at A. So let's give an example here. So let me just look at this one. If this is my polynomial, and it's wanting me to divide by 3, not divide by 3. It's wanting me to plug in a value of 3. So what I can do then is, at this point, X equals 3. That's a root or a solution. Could be, right? It's a possible root, a possible solution. If this was the solution, then the factor would be X minus 3. Right? Think about moving this over and making it say it's equal to 0. So anyways, if X minus 3 is a factor, then 3 is a possible root. So we'd put 3 up in our box to do synthetic division. So the coefficients are 1, -5, 3, and 9. Bring down the 1. 1 times 3 is 3. That's -2. That's -6, which is -3. That gives -9. So a remainder of 0. So what this remainder theorem says is, not only is the remainder 0, this remainder is the value you would get if you plugged in 3 to the equation. Which, again, makes sense, because if 3 is a root, if I plug in 3, I get a y value of 0. That's what makes it a root. But it turns out that it doesn't only work for roots, it works for any number, even if it's not an x-intercept. So look at the one above it. So if I did synthetic there, notice it wants A to be 4. Right, so if I plugged in 4 up in my box, so do synthetic. So this is my x squared term. Remember, there is no x to the first term, so I need a 0 as a placeholder, and then the constant's -3. So if I bring down the 1, 1 times 4 is 4, 0 and 4, 16. So here, I got a remainder of 13, which means 4 is not a root. Okay, but what the remainder theorem says is, not only is 13 the remainder, if you plug 4 into this equation, you will get 13. 4 squared is 16. 16 minus 3 is 13. So that's just kind of a cool thing with the remainder theorem. Whatever the remainder is when you do synthetic division is the same as if I plugged in that value for x. So let me clear the screen here. So knowing that, let's work a few problems. This says, consider the polynomial p of x equals x cubed plus k x squared plus x plus 6. If we want x plus 1 to be a factor, then what must k be? Okay, so here's what we know. If x plus 1 is a factor, then what must be a root? -1 must be a root, must be an x-intercept. Which means if I plug -1 into the equation, into the function, it must be 0. Because in order to be a root, the y value must be 0. That's all I'm saying right here. So let's plug in -1 and set it equal to 0. So that's -1 cubed plus, I'm looking for k, I don't know what that is, times negative 1 squared plus a negative 1 plus 6. And so let's simplify. This would be negative 1. This would be 1k. This would be negative 1. This would be 6. And this must be equal to 0, remember? So negative 1 minus 1 is negative 2. Negative 2 plus 6 is 4. So I've got k plus 4 equals 0, which means the k value must be negative 4. So the reason I could solve this is because once I plugged in negative 1, notice I only had a single unknown. When I have one unknown, I can just solve, get it by itself. So I found the k value, it must be negative 4. So if k was negative 4, then my polynomial would be x cubed minus 4x squared plus x plus 6. And now, like they said, if this is a root, then we need to find the other two factors. So we know that x plus 1 is a factor, which means negative 1 must be a root. So if I do synthetic division with negative 1, that's 1, negative 4, 1, and 6. Let me do this very quickly. 1, negative 1, negative 5, 5, 6, negative 6. So that means that the original polynomial will factor to be x plus 1 was a factor, and then what's left over? This is the constant, x to the first term, x to the second term. So I have 1x squared minus 5x to the first plus 6. And now then I need to find the other two roots from here. So you've got options. You could either use the quadratic formula, because this is a quadratic, or you could factor. If you need to do the a times c method, you can. Hopefully, when the leading coefficient is 1, maybe you can do it just by looking. So this should factor to be x minus 2 times x minus 3. And how did I know that? What multiplies to be positive 6, but when I combine them, adding and subtract them, I get negative 5. That's negative 2 and negative 3. So when it asks what are the other two factors, well, x plus 1 was the known factor. Here are the other two factors, x minus 2 times x minus 3, which means I have x-intercepts at positive 2 and positive 3. So here, the first question, they've graphed this for us. Here's a polynomial. X to the fourth plus 3x cubed minus 28x squared minus 36x plus 144. It wants to know, is 1 a 0? Well, you can look here on the graph. It does not cross the x-axis at 1. So it's not an x-intercept. No, 1 isn't an x-intercept. Is x plus 3 one of the factors? So if x plus 3 is a factor, then that means negative 3 must be an intercept. Because again, think about solving this. If x plus 3 was equal to 0, then x would equal negative 3. It appears it is an x-intercept. So because negative 3 is an x-intercept, then x plus 3 is a factor. Yes, because negative 3 is an x-intercept. See, the graph of P is shown to the right. What are the zeros of P? So I'm just looking, what are the x-intercepts? They're at negative 6, negative 3, 2, and 4. So they're at negative 6, negative 3, 2, and 4. And so if those are all the x-intercepts, which again, it's a degree 4 polynomial, which means it could have at most 4 x-intercepts. So I know there are no complex x-intercepts. And because there are 4, I know they're all degree 1. And what I mean by that is they have a multiplicity of 1. There's no bounces, There's no snakes through. They all just cross. So the multiplicity is 1 of every root. So if I write that in factored form, if negative 6 is an intercept, then x plus 6 must be a factor. For negative 3 to be an intercept, then x plus 3 must be a factor. For 2 to be an intercept, x minus 2 must be a factor. And for 4 to be an intercept, x minus 4 should be a factor. Now just very quickly, we could work through and distribute all this out. I don't really want to do that. But I do want to check, is the y-intercept correct? Okay, so the y-intercept happens if I distribute just the last number to all of these. So let's say if I do that, 6 times 3 is 18. 18 times negative 2 is negative 36. And negative 36 times negative 4 is going to be positive. And so let's say 35 times 4 would be 140. And then another 4 is 144. So that is correct. Again, I know you could just do that in your calculator. I don't have one with me. So just because the end's checked to be 144, which is what I'm supposed to get here, then I'm good to go. Remember, what that means is the y-intercept, the point where it crosses the y-axis, is 144. And so they say make note of this, that P of 0 is 144. 3. Consider the graph of a degree 5 polynomial that is shown to the right, and it's got 5x intercepts. A. Write a formula for a possible polynomial function that the graph represents using C as a constant factor. Okay. So if you had to write a function that has those 5x intercepts, then let's just write the factors. If negative 4 is an x-intercept, then x plus 4 is a factor. Negative 2, then x plus 2. 1 is x minus 1. 3 is x minus 3. And then 5 is x minus 5. Okay, so what they're saying is, think about, you can't shift this graph left or right, or up or down. What happens if you shift the graph left, right, up, or down? You have different x-intercepts. So there can't be any plus here. But now I can stretch the graph or compress the graph because I pin it down at its x-intercepts. Right? They're pinned, and I can compress and I can stretch. So when it says C could be a constant factor, what that means is I could stretch or compress this by any value C that I wanted to and still get those correct x-intercepts. So that's why it says a possible polynomial function. This is a possible polynomial function, but C could be 1, 2, 3, 4, 5, 6, could be a half. C could be anything, and it would still give these x-intercepts. One thing I do know, if you think about the end behavior, though, is because I'm going in this direction, I am negative infinity. As x goes to negative infinity, y goes to negative infinity. And as x goes to positive infinity, y goes to positive infinity. I know that this hasn't been reflected, so I know C has to be positive. Hopefully you see why, because this is the correct end behavior for a fifth degree polynomial. They have to be disagreeing, and they get bigger as x gets bigger, which is the normal, which means there's been no reflection. Anyways, B, suppose the y-intercept is negative 4. Find the value of C so that the graph of P has a y-intercept at negative 4. So we know how to check the y-intercept. We just did it previously. If I multiply all of the constants, they want that to be negative 4. Well, what if it's not negative 4? Well, good news. I can choose any C I want to, because C has to also be multiplied to the values. And so I can change the C to give me an x-intercept of negative 4. So anyways, let's multiply it and see what we get. 4 times 2 is 8. 8 times negative 1 is negative 8. Negative 8 times negative 3 is 24. And 24 times negative 5, that would be 120 negative. So at the moment, the y-intercept is negative 120. But now then, if I multiplied this c at the beginning, if I multiply that negative 120 by some c, I need to get negative 4 as my value. So now I have an equation with one unknown. Solve for c. It's being multiplied by negative 120. So I divide by negative 120. So that's going to be 4 over 12 is a third. That's 1/30. So the c value, the constant that's out front that I need to multiply by, is 1/30 in order to get a y-intercept at negative 4. So again, this would be, if I want the polynomial function, the exact one that gives a y-intercept at negative 4 and the same roots, this is the correct one. I'm just finding the c value. So it's been compressed pretty severely. Hopefully you're kind of getting the hang of this, and you could do some of these on your own if you had to. If I have a polynomial, p, who has zeros at 2, so that would mean x minus 2 needs to be a root, and 2 happens twice, so it needs a multiplicity of 2. Negative 3 means x plus 3 is a root. It happens 3 times, so it needs a multiplicity of 3, and then a root at 4 means x minus 4 needs to be a factor. Find a possible formula for p and state its degree. So here it is. Here's the possible formula. And what would its degree be of this polynomial? If you think about it, I have 3 factors, but this factor is happening 2 times, this one 3 times. So if I were to write this out, and again, you don't have to write this out. I'm just using this as an example. X minus 2 squared literally means x minus 2 times x minus 2. X plus 3 cubed literally means x plus 3 times x plus 3 times x plus 3. Then I'm left with that x minus 4. Now it might be easier to see what the degree would be. If I multiplied all those x's at the beginning, I would get an x to the 6th term, which means it's a degree 6 polynomial. So even though there are only 3 roots, the degree is not 3 because you have roots with multiplicities of 2 and one root with a multiplicity of 3. 5. Consider the polynomial function p of x equals x cubed minus 8x squared minus 29x plus 180. It tells me verify that p of 9 equals 0. So that means if I plug in an x value of 9, the y value is 0, which means 9 should be an x-intercept. So if I could verify that, we could plug in 9 if we wanted to, or we could just use synthetic division. So let's do synthetic, just so we practice the remainder theorem. That's 9, negative 8, negative 29, and 180. So the remainder theorem says I should get 0 as the remainder. So if I bring down the 1, like I did there, okay, 1 times 9 is 9, negative 8 and 9 is 1, 1 and 9 is 9, that's negative 20, that's negative 180, that's 0. So the remainder is 0. That means what must be one of the factors? That x minus 9 must be a factor. So that means that the polynomial in factored form would be x minus 9 times, and then look at my new depressed polynomial here that I got as my answer. So the constant is negative 20. This is x to the first and x to the second. So I have a quadratic, x squared plus x minus 20, that I could either factor or use the quadratic formula to find the other 2 roots. Hopefully you can spot factor this as x plus 5 times x minus 4. Again, what multiplies to be negative 20 but combined is a positive 1. It's 5 and 4. And so my remaining 2 factors would be here, x plus 5 and x minus 4. What are the zeros? The zeros would be at 9, at negative 5, and at 4. You get that just from solving here. And then D, sketch the graph. So you're not going to be able to get exactly the graph correct, but you can get a sure enough, close enough answer. Okay, so if I have, let me change where my y-intercept is. Not my y-intercept, my y-axis. So again, if I'm somewhere here, I know I have roots at -5. I have another root at 4. And I have another root at 9. Because the leading coefficient is positive, I know this is going to behave like an x to the third would, which means it's going to be down over here and up over here. There's been no reflection. And I also know the y-intercept must be at 180. So again, we can just pick some scale. I'm not going to spend a lot of time, but say we went by 20s. I don't know if this is exactly right, but let's pretend like it is. So now my y-intercept's at 180. So the graph would start down here. It's going to cross here because it's a multiplicity of 1. Then it has to come up here and then start going down. Cross again, multiplicity of 1. Then it has to start back up. Is this exactly what the graph looks like? Probably not. But this is a possible solution, a possible graph. And it's got all the key characteristics. A, verify that p of -1 is equal to 0. So if I need to verify that, we could plug in -1, or we're going to use the remainder theorem here. So this would be 2, 3, -2, and -3. And I need to get a remainder of 0. So I bring down the 2. That's -2, that's 1, that's -1, that's -3, that's +3, and 0. So that means what must be a factor? If -1 is a root, then x plus 1 must be a factor. So I know that this must factor to be x plus 1 times, and then what's my new depressed polynomial here? 2x squared plus 1x minus 3. And now then I need to factor this. So this one might be a little bit harder to factor because the leading coefficient is not a 1. So it's not as easy to spot factor. So I'm going to do a times c this time. So if you struggled factoring to this point and you don't know how I've got those answers so quickly, then you need to factor the way I'm fixing a factor every single time, doing the a times c method. So this is my a, this is my c. 2 times 3 is 6. Now I want to know what can multiply to be 6. 1 times 6 or 2 times 3. So now out of those, they need to be different signs because they need to multiply to be negative. So different signs to give me negative, but combined to be a +1. That would be a +3 and a -2. So I'm going to rewrite the middle term as a +3x and a -2x. So I'm going to go -2x plus 3x minus 3. Now, if you did it in the other order, that's fine. The order of the -2x and the +3x doesn't matter. That's totally up to you. And now then, the way we factor doing the a times c method is we group. So I'm going to group the first two together and the last two together. The GCF of the first two parentheses is 2x, which leaves me with x minus 1. The GCF of the last set of parentheses is a +3, which leaves me with x minus 1. Since the parentheses match, that means grouping has been successful. So this factors to be, remember the factor that was already out front, x plus 1. And then what's in front of the parentheses, 2x plus 3, times what is the matching parenthesis. The matching parenthesis here would be x minus 1. So that would be the other two factors, 2x plus 3 and x minus 1. So now C, state the zeros. So again, if x plus 1 is a factor, then -1 must be a 0. And then x minus 1 is a factor. That means +1 must be a 0. And then here, this is the weird one now. 2x plus 3 is a factor. So I set that equal to 0 and solve. 2x equals -3, which means x would have to be equal to -3/2. Another way we could write that is -1.5. So those are the zeros. Those are the roots. And now then we want to sketch a possible graph. So again, we know the leading coefficient is positive, and it's a third degree polynomial. So here's the end behavior. We know that it has to cross at negative 1.5, which is here. It must also cross at negative 1, which is here, and at positive 1, which is here. And we know there's a y-intercept at negative 3, which is here. So again, the graph's going to be something like starting down here, and it's going to cross just for a second, turn back down here, and then cross again. Again, this is just a possible graph. Doesn't necessarily look exactly like this, but this is possible. It has the correct y-intercepts, the correct end behavior, and the correct x-intercepts. Okay, go ahead with the time that's left in class. Try to do the homework problems. And I'm going to go ahead and put those answers up right now. So pause the video. Okay, here those are. Here's the answers. I'll let you look over that. If you have any questions, you can send them to me. It kind of fits with everything we've been doing to this point, so maybe you're not going to have any questions here.